we will see today, so yesterday we were seeing the low pass filters. Today we will see the high pass filters and band pass filters. So these filters, one of the characteristics is that the sum has to be zero. So the sum here has to be zero. So they are typical filters are symmetric. So they have some kind of symmetry. So when you see this kind of filters, you can imagine that they are symmetric. So this is H bar, this is bar. Or also they can be, so this is odd symmetry. They can have even symmetry, and then they have this kind of shape. Let's say very bad at both of these. Somehow all the area has to be zero. Okay, so all this area has to be zero. The same here. So all these areas have to be zero. H of 0 is 0 in both cases. Okay, so let's see that. So let's see now how to do this with images. Okay, so here we go. So let's see the ideal high-pass filter. So the ideal high-pass filter, it is the opposite of the ideal low-pass filter. So it is 0 at low frequencies and then 1 everywhere else. And if you compute the impulse response, the point spread function, this is the response in 2 dimensions, and if we make a profile, this is how it looks like. So here we have superposed the frequency plot and the spatial, the real space plot. Okay. We take this image, we multiply by this filter. This is the power spectrum of this image. So we multiply by that. This is the result of the multiplication. So the multiplication in the middle is 0, and everywhere else we keep whatever we have. And then this is the effect. And this star here, what says is that we have positive and negative values. So because of this 0 property, you may look at the output image. So the output image, so let's make it right again. So the output image at 0 is whatever we had at 0. So those are Fourier transforms. But this is 0. This is 0. So the whole thing is 0 again. So that means that the mean of the output image is 0. So it needs to have positive and negative values. And then this star here, simply saying, okay, the image has positive and negative values, but we have rescaled them to be between 0 and 255 for just for representation. Okay, so for representation, we scaled them to 0 to 55, but originally the data, the image had 0 mean. And yeah, high-pass filters, you may remember that edges require high frequencies. So the high-pass filters are edge detectors. Okay, ideal band pass. So the ideal band pass, yeah, how to construct it, this is interesting. Okay, so let's say that you have a low-pass filter and you want to construct a high-pass filter. Okay, so let us write that. So I will So the Fourier transform of a low pass filter is that one. Okay. So once I have that, how can I construct the frequency response of a high pass filter? Okay, I can simply say this is 1 minus the low pass filter. Okay. 1 minus the frequency response of a low pass filter. You see, if you take 1 and you subtract this part, this is what you get. Okay, so I can construct my filters in that way. With transforms everywhere. And now, let us do the inverse Fourier transform. We do the inverse Fourier transform. Okay, so the impulse response of a high pass filter now is a function of space. Okay, here we are showing in 1D, but it also applies to multiple dimensions. So that's pretty close. Okay, so what is the inverse Fourier transform of 1? The delta. Okay, so this is a delta at R minus the impulse response of the low pass filter. And the impulse response of a low pass filter, we already know it is kind of zinc, or zinc in 2 dimensions. This is 2 dimensions. This is 1 dimension. Let us look at this. So it is delta minus the zinc. You see, delta and the zinc is inverted. So a high pass filter is a delta and then minus a zinc. Okay, good. Then band pass filters, I can construct band pass filters in a similar way. So let's go back to here. So if I want to construct this band pass filter, I can do it. Let me do it here. So I can do that band pass filter. I will use different colors now because I'm running out. I want to highlight 2 different filters. So I can have a filter that is this one that goes to omega 2. And I can design this filter that goes to omega 1. And then I have to subtract 1 minus the other. So it would be my band pass filter would be the impulse response of the low pass filter smooth minus the impulse response of the frequency response of the band pass filter 1. So those are 2 sinks. So it is at the end, it is here. We do the spatial analysis in real space. This will be a sink, let me do it in 1 dimension that you know, associated to omega 1 and omega 2 minus the sink associated to omega 1. Which one is wider? Let me remove the vector because we have done in 1 dimension. We have done it in 1 dimension. And we are not too specific about the constant syndrome, but we don't care. Okay, which one of the 2 is wider? Omega, the zinc associated to omega 2 or omega 1?
No.
Omega?
1.
1 is wider. Why?
Because we said that when we with the Fourier transform, the wider the signal is, the
Smaller.
the smaller the Fourier transform.
Yeah. So this one here, omega 2, would be something like this. While omega 1, omega 2 is blue. So it's something like this. While omega 1 is something like this. Okay, so we are subtracting this minus that. Okay, then so this is what we are doing now, but in 2 dimensions. So we have a wider low pass filter minus a narrower band pass filter. And then the disk in between will be my band pass. Okay, so here you have the example. So you have which of the two has a narrower band cutoff frequency. So both are low pass filters, but one has a cutoff frequency that is smaller than the other one. Which of the two is smaller?
The second one.
The second is smaller because it is much smoother. Okay, so there are much more frequencies here than there. Okay, so now we subtract the two, and that is what you get. Okay, so this would be a band pass filter. And here's a representation of the power spectrum. And this is another example, but now with narrower bands. And I think this is a good point to show you this with stop sharing. Let me share with this one. Okay, so now let's start sharing. Okay, so here we have our favorite image, and let's see frequency filters. Ideal. Okay, so we can design low pass filters, for instance. We can define low pass filters, and then we have cutoff frequency that we can add. You can see this is the impulse response, and this is frequency. This is real space. Okay, so the smaller it is in frequency, the wider it is in real space. And now you start recognizing this repetition. You see that I mentioned that when you do the convolution with the Fourier transform, the Fourier transform is repeating the images all over the place, so it is making them periodic. And you see these corners here, they are caused by the you have a Y PSA, a Y impulse response, and then the nearby impulse response is coming into your copy. Okay, it doesn't happen, but it does happen, but these are so much smaller that you don't notice. You see. Now you see a little bit of ringing, right? Not so much. I can see it on the screen, so you can see it too. Can you see the ringing? So the ringing from the nearby copies, they are also coming in, but they are so weak that you don't see. But if they are strong enough, and here they are strong enough, you see these corners, and these corners are caused by the invasion of the nearby copies into your field of view. Okay, so then let us apply it. Okay, so let's keep this one. So now we have, so this is the original image and this is the low pass filter. What else do we have here? So it is the same, but now with the different bands. And the same, but now we are in the power spectrum. So this is the original image, this is the module of the Fourier transform, this is the phase. And then this is the module of the filter image. So all the regions outside the filter has been set to 0. And then the phase. When you see the phase, you have whatever phase you had, and then 0 phase. What is the phase of a real number? 0 or 5 or 180 degrees. Okay, then these are low pass filters, these are high pass filters. Okay, so in high pass filters we have the opposite. So let us execute this one. So now you can see that even this high pass filter, we are removing only a little of the Fourier spectrum, and the filter image is quite different. You see, and we haven't removed so much. But high pass filters, they are really strong. So really strong in the sense of what is the appearance change. So we can try to remove even less. Okay, so now we are keeping a bit better all these details. Okay, but we haven't removed almost anything. You see that the cutoff frequency is really low. High pass filters are often used when you have a gradient of illumination, for instance. So let's say that a part of the image, so let's say that this part is a bit brighter than this one. But so this is so low frequency, so you can imagine this is, you have only one period or half a period. So if this is brighter than this, you would have only one period. And then this is really low frequency. And then you use a high pass filter to get rid of gradients. And what we can see is what is the impulse response of these things. So you see, it is almost a delta. And yeah, so let us now remove much more. How I remove the ones I don't want. Yeah. So let me close this one again. Load the image. Okay. Now we do the high pass filter again. High pass filter, but now with higher. And this is interesting. So for instance, we are keeping more than half of the spectrum, but we barely see anything. See? We cannot see much here. Okay, why is that? I think that there is an interesting yeah, okay, I will explain it later on the whiteboard there. Okay, so then band pass filters. Okay, so we can have a band pass filter. Let me close the ones we don't want. So I don't want this one, this one, this one. And execute. Again, you don't see much. It is at middle frequency. So if you want to see something, you can see some edges here. And if you want to see something, you have to make this relatively low. So at this, probably we will see something. So this we don't want, this we don't want. Now you start seeing some details, but they are really low frequency, you see. So it is a very narrow band, but at very low frequency, and then you see something. each one of the bands. And these are details of a particular frequency and size of the detail. They are very much related. Okay, so once you know the size of a detail, automatically, so this is kind of single sign in a way. So it is so narrow that it is a single sign in all directions. You may remember now the Fourier transform and the waves that we have. So we have only very few frequencies, so all of the signs are more or less of the same periodicity. And then the length, the wavelength of that wave defines what is the length of the objects you will see. And keep this image in mind, because I want now to go to the whiteboard again, and I will make a couple of comments. Let us take one. Okay, so I take one of these. So you may remember this is in real space. This is a wave that goes like this. And it is like a kind of flat wave going in that direction. So that's a wavelength. So this is half the wavelength. Okay? This is lambda divided by 2. And the whole thing is lambda. So from here to there it is lambda. If you take one of these, this is lambda divided by 2. Now, think of the Fourier transform at that point. What is that? At a particular frequency, okay? So only one frequency. Let me make my frequency blue. Okay, so my frequency is blue. So I'm only considering that frequency. So now what is that? Okay, it is the input at that frequency times the impulse response at that frequency. Okay. But let me write it and then I will simplify. But this is one. Okay, because it is at the particular frequency that is one. Okay, and so what that means is I'm keeping only the coefficients coming from these frequencies that are within this region. So I'm keeping all the, you may remember that these had an amplitude, and they had a phase. So the amplitude was how wide this was, and the phase was whether I should shift it to the left or to the right. And then this is, so at that particular frequency, it is the inner product of your input image, this is your input image in real space, times the complex exponential. So that is why I was saying what you see are details of a particular wavelength, of a particular size. What we are doing is, okay, what is the inner product? So what is the superposition of your input image with this wave? And this wave has this size, this characteristic size. So that is why we see objects, when you do a bandpass filter, you see objects of that particular size, of a size that is lambda half. And yeah, this was some interesting idea. The other one was this. Okay, you may remember that when we did the high pass filter, so let us send here again omega x, omega y, and we have this high pass filter. So the shaded region is the one that was going through. So this is 1, this is 0. And we barely saw anything. So why is that? And the reason is that if you analyze what is the power spectrum this you already know what it is. The power spectrum of an input image. I'm doing it in one dimension because those are the ones I can draw easily. Looks typically they look like this. So they normally behave as 1 over omega squared. So that means that if you do a high-pass filter and you keep only this part, you're removing most of the energy of the signal. And that is why we barely saw anything in the high-pass filter image. If you move it closer to the origin, more and more energy is kept, and then you see something in the output. Okay, good. That's fine, but they have a problem that because of this uncertainty principle, they have ripples. Yeah, this idea has appeared already. So they have ripples. So if you put an ideal low-pass filter, you have a lot of ripples that extend to infinity in principle. But yeah, at some moment they're so small that we don't care about them. And if you filter one of this image, for instance, with an ideal low-pass filter, you see ringing. So this is annoying. And this ringing, we understand where it is coming from. It is the convolution of the point spread function, so the impulse response in real space, with this signal. And then we see the ringing caused by the ringing of the impulse response. But this is, we don't want this. Okay, so we may wonder, okay, what is the filter, what is the shape that has the best compromise trade-off between spatial support and frequency support. So this uncertainty principle, whatever this formulation I don't like. These are specific constants and so on. I think that they are not so well defined. But yeah, there is another way that is much better to define it. But however you define it, what it says is, okay, this is somehow representing the spatial support, this is representing the frequency support, and it is larger or equal something, which is the filter or the signal such that we get closer to this bound. It is larger than something, but you can be closer to the bound or further from the bound. So which is the one that gets closer to the bound? And that is the Gaussian. So the Gaussian is the one that gets more or less as close to the bound as possible. And then it follows the same principle in the sense that if a Gaussian is wide in frequency domain, it has to be narrow in the space domain. But the product of the two supports is the smallest one you can have. Okay? In that sense, it is called an optimal filter. And it turns out that the Gaussian doesn't have any ringing. Not at all. The inverse Fourier transform of the Gaussian is another Gaussian. And it is still, yeah, this is the formula of the one-dimensional Gaussian. We may recognize the features of T. So this is the mean. The mean is the mean value here, and then sigma controls what is the width of that Gaussian, that shape. And this is the expression now in 2 dimensions. So it looks more complicated, but actually it is not so much. So you have. And in this example, he's particularizing a particular kind of Gaussians, but we will give now a more general expression for the 2-dimensional Gaussian. So you may center it at some location, mu R, mu C, so this is the center, so you can shift this Gaussian to wherever you want. And then you have two sigmas, so you have two standard deviations, one for the rows, another one for the columns. And then you have to, this normalization factor is to make the integral to be 1. And I think that's mostly it. Okay, so what is the more general expression? So these Gaussians here, they are necessarily round or at least aligned with the axis. So you can construct with that expression, you can construct Gaussians that are round, that have this shape or this shape, but you cannot make this shape. Okay? So how to get that shape? Probably you already know. So let us name the axis. So this is x, this is y. So those are representations in real space. Okay, have you studied the multivariate Gaussian in statistics? No? Okay, so the multivariate Gaussian. So you have two, so let us consider x and y as a vector R. You can do it in more dimensions, but 2 dimensions are easy. Then, based on this R, you have a variable that has a multivariate Gaussian that follows. This follows a multivariate Gaussian of mean mu, that has to be a vector because it has to be this point where things are centered. And then sigma. Sigma is a matrix now. It will be for 2 dimensions, it will be a 2 times 2 matrix. And it controls the orientation and shape of that Gaussian. So how is that? Okay, so the probability density function of R is 1 over 2 pi and sigma. This is the determinant of that matrix. And all this is to the power d. D is the dimensions that we have. So here d is equal to, because we have 2 dimensions, d divided by 2. And then the exponential of what? -1/2, and then r minus mu transpose sigma minus 1 r minus mu. Okay, let us study these things. Okay, so R is a 2 times 1 vector. Okay, so this is 2 times 1. This is a matrix, so this is 2 times 2. This is 1 times 2. So the whole thing is 1 times 1. This is a scalar. That is what you need for an exponential function. So this is well constructed. And then this is the normalization factor to make the whole thing to have a volume of 1. Okay, then this matrix here. Okay, so this matrix here, we take this matrix and it has sigma x squared, sigma y squared. And that is the one, if you put zeros here, and those are the ones that the slides are showing, then you can achieve this kind of Gaussians. So those are Gaussians in which the 2 variables are independent. But these Gaussians, x and y, are not independent. Okay, so then you need something else. So the something else that you need is a sigma that allows having correlation. So this will remain the same. And then you have the correlation between sigma x and y. between X and Y. Okay, and this is the one that gives you this kind of representation. Okay, so now you can have Gaussians in any orientation. So you are not constrained to construct Gaussians that are circular or are aligned with the axis, but you can orient them in any arbitrary direction. This is very useful to make directional analysis. So let's say that you have an image and you want to analyze what is happening in this direction. And then you can use this kind of Gaussians that are elongated to see what is happening in that direction. Okay, now you apply your Gaussian filter, and because the impulse response doesn't have any ringing, now the output doesn't have a ringing either. And you can compare to the ideal low-pass filter, where you have some ringing. Okay. How to construct Gaussian low-pass filters? Okay, so what you say is that instead of having X and Y here in real space, I construct a Gaussian. So we call this, instead of having a Gaussian that depends on the spatial coordinate, we have a Gaussian that depends on the frequency coordinate. But the concept is the same, simply that you have to, this will be the omega frequency. Typically, you want the Gaussian to be centered at 0, so this is simple. So this mu is 0. And this will be your low-pass filter. So my low-pass filter omega will be a Gaussian for when this is expression. And I only have to define what is the sigma matrix, what are the cutoff frequencies somehow. Okay, so then, here you have an example where you have a Gaussian in Fourier space, the corresponding real space response. Here in this example, they more or less coincide in width. And if you make that bigger in Fourier space, then you are convolving with a smaller, with a narrower real space response. And then here you have some examples. So original image, then the original power spectrum, this is the filter that we want to apply. And then this is the output. And we say that we are convolving this with the Gaussian, and this is the result. How to construct Gaussian high-pass filters? Okay, this is very easy. Now we know all we have to do is 1 minus the Gaussian, 1 minus the low-pass filter. So this is 1 minus the low-pass filter, and then you have a smooth transition between 0 and 1 given by the Gaussian. And what is the impulse response of that? So it is delta minus the impulse response of the low-pass filter. But the impulse response is a Gaussian, so now it is a delta minus a Gaussian. So the original image, the power spectrum, and then the filter we want to apply, and this is the result. And now the Gaussian is wider, so if it is wider here, we are removing more frequencies and we should see less, and that is what's happening. So we see less the details than here. We see many more details there because we are keeping much more energy. You may connect this idea that we had before. The same applies here. So now we are using Gaussian filter, but the idea is the same. So this Gaussian filter is removing the low frequency. So it depends how wide this Gaussian is. You're removing more or less energy from the image. And Gaussian bandpass filters. Okay, so they're not difficult now. We understand how they are done. So you have two low-pass filters and you subtract them, and then what you have is a bandpass filter made with Gaussians. And so here we have a strong low-pass Gaussian low-pass filter, a milder Gaussian low-pass filter. We subtract this one, so this one minus this one, and then this is the result, bandpass filter. This is the power spectrum, the impulse response. So here we have both are, the impulse response of the two Gaussians, they are Gaussian. So here what we have is so you have a wide Gaussian minus a narrower Gaussian. So it looks at the end, it looks something like this. So you have something like real space. So in real space, we have a wide Gaussian, and then minus a narrower Gaussian, so something like this. It has to be wide because the higher, because the height has to be, the area has to be 1 in both cases. Let us label the axis. So this is 1 of R, 2 of R. And then the subtraction is something like this. So those are, sorry. The subtraction is something like this. It doesn't go up. You can check. It goes like this. See? Doesn't overshoot. Yeah, these things when you have a response, let us label of this. When you have this kind of responses, these areas here, they are called overshooting. So it doesn't overshoot here. The Gaussian, the bandpass Gaussian doesn't overshoot. Okay, so there are some more examples with different widths and so on. Okay, so I think it is time to make a break. Okay, so let us compare ideal filters with Gaussian filters. Here we have an original image, and here we have the result with an ideal low-pass filter and an ideal high-pass filter. And let us compare to the result with kind of equivalent cutoff frequencies with Gaussians. So you may notice, particularly here, it is particularly visible. There is a kind of ringing. You see that there is a kind of waves on top that disappear when you go to the low-pass filter, to the Gaussian low-pass filter. You see? So this is the ringing by the ideal low-pass. And in the high-pass, it is the same. You have this kind of same ringing. So you see dark, dark, dark. And when you go to the Gaussian, it disappears, this ringing on top. Yeah, the ideal bandpass filter, and again we see this kind of ringing on top, and the equivalent Gaussian doesn't have it. Okay, what about the power spectrum? Okay, so let's say we have an original image, and then we have the power spectrum, the phase of that image, and then when you do a low-pass filter, you are keeping the central region of that power spectrum. And you may remember now this 1 over omega squared that typically images have. So you are keeping the energy mostly in this region, but the Gaussian never goes to zero. So that means that okay, the amplitude is very small, but the phase are still conserved, and this is very interesting. Okay, let us look at the phase of a frequency component. Okay, so we have the output. Let's make it red. So we have the output. The particular frequency is the input at that frequency times the impulse response, or the frequency response. Okay, now let us express this one as an amplitude that depends on frequency, and then a phase that also depends on frequency, times the filter. But the filter, it is a Gaussian filter. So if it is a Gaussian filter, this is a real number. And if it is a real number, it is just a scalar. It doesn't have phase. So it will be this thing. But let us now write where they belong to. So this is a complex number, and this is a real number. So because it is complex, we can decompose it into a real number here. This is the one that has the complex, and then this is real again. So now I can group these two. I can group these two into A omega H omega, and then a phase. And again, this is real, and this is the complex part. Complex meaning both real and imaginary parts. So now let us compare. So what is the phase? What is the phase of? What is the phase of I? The phase of I is phi, and the phase of X is also phi. Oops. Phi. And now it comes a very interesting thing. That is, Gaussian filters are only affecting the amplitudes, only. The phases are kept the same. And also, you may remember, where is the important part of the information of an image? It is in the phase, it is not in the amplitudes. So we are controlling the amplitude, but the phases are kept exactly the same as in the input. Okay, so that is why in the filter image, okay, it is blurred, but the phases are exactly the same as the phases of the original image. The amplitudes are not, because the amplitudes are multiplied by something. But the phases are the same. And what else? Here you see phases are the same. Yeah, there are some small differences, but they are. Oh no, but this is of a sharpened image. Okay, so what is a sharpened image? We didn't introduce that. It is very easy. Okay, so we have said high-pass filters, they get edges. Okay, so if I construct an image that is, let's make in real space. I construct an image that is an input image composed with a high-pass filter, then this is somehow detecting edges. Because high-pass filters are edge detectors. Okay, what happens if now I construct a new image that will be eye sharpened? That is the original image, that is X, plus this, thing, this X of R, involved with the edge here. So what I'm doing is the original, so I'm doing the original plus the edges of the original. Plus the edges of the original. How does it look like? So you have here the original, and now the edges of the original on top. You see more details. Why? Because our visual system likes details, likes edges. So we see much better this sharpened image than the previous one. Yeah, and then the face is changing a bit. And yeah, just for you to get some hands on this. So let's say that I want to express this as a single filter. So instead of having, what is this model? Okay, so I have an input, and then it goes through a high-pass filter, and I'm adding it also, and then I'm getting eye sharpen. This is my model. So now, can I express this as a single system? So can I construct a system such that it goes into my system and it goes eye sharpen? Or I always need this loop around. So what is H prime? Do you think we can or no? All you have to do is to express this as a single convolution. So if you express that as a single convolution, you have X of R convolved with the delta plus the high-pass filter. So you can do it in a single step. So it would be a delta plus this. What is that? In Fourier space. So this is H prime. If we look. So this is H prime. So what is the Fourier transform of H prime? So this is a high-pass filter. So let's say it is a Gaussian high-pass filter. So Fourier transform of this would be something like this. I will write formula and we'll make it flowing. Omega. So instead of it starts the delta, the Fourier transform is 1, and this, the Fourier transform is whatever that is. Okay, but so it is 1 plus something. So 1 plus something is something like this, for a Gaussian. So if this is Gaussian, if the high-pass filter is Gaussian, it is something like this. And we can compare to the high-pass filter around. So the high-pass filter around is the same filter, but this one is removing H of the HPF at 0, so it is removing the details, so the low frequency component, sorry. While this one is not. This one is keeping H prime at 0, 1, so it is keeping. So it is whatever I have plus the edges, and the blue one is just the edges. Okay. Any question?